Bismillahirrahmanirrahim. Assalamu alaikum. It's our 26th lecture of Advanced Electromagnetic Field and Waves, and in this lecture we are going to discuss some short questions related to waveguides. Okay, so the first question you have is the for a good conducting waveguide, which component of E and B are zero at the surface of the conductor? So, so as this is a good conductor, so the tangential component, he is saying that which components of E and B are zero. So for the case of E, for good conductor, the tangential components of E field are zero. But for the case of B, for good conductors, the normal components of the B field is zero. So you have to remember that for a good conductor waveguide, the electric field tangential component is zero. And for the case of B, the normal components of the B field is zero. Okay. The next question is write out the differential equation for any component of field should satisfy in a waveguide for a mode propagating down axis as e power iota kz with wave vector k. So you have to write the differential equation that basically any component should satisfy the waveguide. So you know that while solving the waveguide, you will start with a differential equation which we derive from Maxwell's equations or Helmholtz equations, and that equation is basically this: del square psi plus k square psi equals to 0, whereas psi either be electric field or either be magnetic field. You know that in case of TE mode, your Ez component is 0, then we have to take del square h plus k square h equals to 0. In case of Tm mode, your hz is equals to 0, and then we take our differential equation as del square Ez plus k square Ez equals to 0. So this is basically the differential equation which we are using to take for any components of the field that should satisfy the waveguide. Okay, whereas del square is the Laplacian. For solving the rectangular waveguides, we use the rectangular coordinate system, and for solving the circular cylindrical coordinate system, like an example, if you are solving a circular waveguide, we use the cylindrical uh, Laplacian. Okay, whereas k is basically the wave vector along the propagation. Next question is a waveguide mode has a cutoff frequency omega lambda. Okay, a waveguide has a cutoff frequency omega lambda. If a wave is coming with frequency omega are sent into the waveguide. So there is a waveguide which has a cutoff frequency omega lambda, and an electromagnetic wave is coming to that waveguide with a frequency of omega. With which propagation vector do they propagate? You know that the propagation vector can be write as kz square plus kc square, where kc is the propagation of the cutoff and kz for the waveguide, any propagation of the waveguide. Okay, so for the case of if omega is greater than omega lambda, what it says means that the incident frequency of wave is greater than the cutoff frequency above cutoff, then your wave propagates and kz is real. As kz is real, so this goes to other side and minus, so it becomes kz equals to under the root k square minus kc square. But in the case if lambda is smaller than omega lambda, if cutoff frequency is greater and the incident wave frequency is low, what happens? Then your wave will not propagate, and in that scenario your kz is imaginary. So in that case your uh, kz goes here, sorry, kz remains here, and this uh, kc goes to the other side. Okay, so here you can see, kc is here and that other vector goes to the other side. And here for this scenario where omega is greater, so k is here, omega kc goes to the other side, and this is minus sign, but here kc is here and here is iota sign because kz is imaginary. So if your incident frequency is greater than the cutoff frequency, you can say your wave propagates and kz is real. And if your incident wave frequency is lower than the cutoff frequency, then your wave will not propagate. This is the answer. So our final question is basically a cylindrical resonant cavity with end z equals to 0 and z equals to d. You have a cylindrical resonant which has a cavity, and at the end boundaries at z equals to 0 and z equals to d is oscillating in TE mode, transverse electric mode. Which electromagnetic field component determine all the components? So in TE mode, you know that your electric field Z component equals to 0. There is no electric field Z component. So you can say Ez equals to 0. So he says that which electromagnetic component determines all the components. So if Ez is 0, so the electric field components can be determined by Hz components, because in TE mode there is Hz components. There is no Ez components, and in TM mode there is no Hz components. They are all Ez components. Okay, this is inverse. TE mode is the inverse of the TM mode. So that's all for today's lecture. We solved some important questions relevant to paper for a topic of waveguides. Thank you. Allah Hafiz.